Alright, hello again. The wind's picking up now, so hopefully the audio's not suffering too much. Just one more word about the trig identities. This whole process for us was quite long-winded, partly because I'm doing extra explanations as we go, but there is an identity that says cos of 2x would equal 1 minus 2 sine squared x. That's something you could look up. I've got my trig identities here. I need to make a bit of... I want to keep those. Let's just make a bit of space. Sorry, it won't take long. If I'm looking at the double angle identities, where are they? Here, double angle formulas. Cos of 2 theta is 1 minus 2 sine squared theta. That's the one that we ended up at, right? And you could just look it up and plug it straight in from the start with that question, right? Anyway, let's get back to work because we need a sign diagram for this first derivative. Let's draw that. And then we have to do a sketch of the function. So we're going from 0, so our interval 0 to 2 pi. Don't need it to be that big. To 2 pi. Let's try and use the stylus pen again. 2 pi. This is a sign diagram of the first derivative. These sections are blanked out. Okay. We're at pi on 6. Right, first solution where f prime x equals 0. 5 pi on 6. And the third one was 3 pi on 2. We need to test that region, that region, that region, and that region. And this is where my trusty unit circle is going to help. All right, what's a nice value that I could test in my first derivative between 0 and pi on 6? And for me, the easiest point would be 0. I want to know, is my function increasing or decreasing? Am I going uphill or downhill in this space here, right? So if I test the angle of 0 in my first derivative, right? Well, the cos, right, of 2 times 0 is just 0. That equals 1. Cos of 0 is 1 times 2, it's 2, minus sine of 0 is 0. So I'm ending up with something that is positive there, right? Positive. Okay. Now in this space between a pi on 6 and a 5 pi on 6, what's a nice angle to test? It would be pi on 2, right? Cos values for pi on 2 are 0, sine values are 1, okay? So in my first derivative, all of that will become 0. The sine of x will be 1, but then it's times by negative, so that will be negative. Okay. In my third region, what's a nice value to test? Needs to be between 5 pi on 6 and 3 pi on 2. It's going to be here, isn't it? At pi. Right. So pick out the angles that are easy to test. Okay, cos equals minus 1, so that will be negative. So that's all 0, right? So what you're getting there, oh no, it's not going to be negative because we've got 2x, right? I didn't have to worry about that when we were testing the angle of 0, but if I'm plugging in pi into this function, right? X is pi. We've got 2 pi, 2 times pi. So I'm actually looking at this spot over here on the unit circle where the cos value equals 1. 2 times 1 is 2, that's positive. And then I minus away the sine of pi, which is 0. Right, so this is positive. Okay, now I need to test in here, and I think the easiest one to test is back on 2 pi. All right, so I need an angle in this space. All right, it's got to be bigger than 3 pi on 2. And I'm going all the way up to 2 pi because these numbers are easy to work with, ones and zeros, right? So, going to my first derivative function, cos of 2 times 2 pi, that's the cos of 4 pi, right? That's 2 pi. Another time around the circle, 4 pi, so that'll be 1, it'll be positive. That'll all be positive. The sine at 2 pi is 0, and so this actually ends up being positive. Okay. Now, what kind of shapes have we got here? If we're going from positive gradient to 0 to negative gradient, we must have a maximum. Here, we must have a minimum. What happens when we go from positive to 0 gradient to positive? Well, we must have a stationary point of inflection. Right. So that's what's happening, and you would need to make a list of that. Right. So you could say there's a local max. Local max. Right. At this point, x equals pi on 6. Not sure what the y is yet. We've got a local min next, where the x value is 5 pi on 6. And we've got a stationary point of inflection. If I just write stat put inflect, stationary point of inflection at 3 pi on 2. Okay. What about the corresponding y values? Well, when we have x equals to pi on 6, right, we need to think about what point would that be on our original function, right? You may want to actually do this on a calculator. I won't write that. All right. What value does the function give us at pi on 6? Okay. Well, sine of 2 times pi on 6 is root 3 on 2. And we've got 2 times cos pi on 6. Right, so cos pi on 6 is also root 3 on 2, but we've got 2 of them. That's 2 root 3 on 2. So that will give us 3 root 3's on 2, or 1.5 times root 3. And I'm actually going to reach for the calculator at this point. We'll just use a decimal approximation, I believe, would be the best thing to do. So 1.5 times square root 3. And it's telling me that that's 2.6 approx. Right. So we're approximately, right, whoop, I'd rather do this in black. We're at approximately 2.6 for this max, okay? So the min's probably going to be the negative of that, given the symmetry of these functions. Let's have a look at that. Right. So 5 pi on 5 pi on 6. What's the function giving us when the x is 5 pi on 6, right? Well, the sine of 5 pi on 6 is needing to be doubled, right? So it actually be sine of 10 pi on 6. Now that's going to be minus root 3 on 2. This one might be a bit harder for you guys to see. What's 10 pi on 6? Well, that's the same as 5 pi on 3, isn't it? Okay, there's 3 pi on 3, there's 4 pi on 3, there's 5 pi on 3, it's here. All right. So our 10 pi on 6, after we've doubled, it's the same as 5 pi on 3. All right, what's the sine value there? The cos value is a half, but the sine value is minus root 3 on 2. Okay? And then we're going to be doing what? Plussing 2 times cos 5 pi on 6. Cos 5 pi on 6 is here on a unit circle, and the x-coordinate, or the cos value, is minus root 3 on 2, but we've got 2 of them, so we're doing minus 2 root 3 on 2. That all equals minus 3 root 3's divided by 2, and that's going to be approximately equal to negative 2.6. Okay, the last one we need to think about is, what does our function give us when we put in 3 pi on 2? Okay, so start with the sine of 2x. Well, okay, 2 times 3 pi on 2 is 3 pi. What's sine of 3 pi? It's 0. Oh, great. That was nice and easy. Cos of 3 pi on 2. Cos of 3 pi on 2 is also 0. This whole thing actually just equals 0. Good. That was an easy one. Right. Now, to do a sketch, I also want to know where will it start. It starts where our x's are going down to 0. That's a y-intercept. Y-intercept. Right? Where x equals 0. And the value for that would be, okay, let's make 0. Sine of 0 is just 0. Great job, sine. You can take 5. Cos of 0 is 1. 1 times 2 is 2. So the y-intercept is at 2. Okay, and we've got enough to sketch for this question. This question wasn't asking about points of inflection or where does the function equal 0. So, the points where it crosses the x-axis. It's just looking at the maxes and the mins. Okay, but we are using them to graph the function, and we know that it starts 2, goes up to 2.6. Maybe I'll put my 2 here. All right, and we're going, our maxes will be at 2.6. The min's going to be down at minus 2.6. Right, that's 0. We're starting here, we're going up to 2 pi. So I draw that on first. I go about halfway, that's pi. Okay, I know my max will be at pi on 6. It's coming in a 6. How many squares did I do? 1, 2, 3, 4, 5, 6. That's nice. So the max is going to come in here. Right. Where x equals pi on 6. The minimum is at 5 pi on 6. Right, that's here, 5 pi on 6. And that point there, and it's down, approx here, so there's a minimum. Right, this is a maximum. Right, and halfway between pi and 2 pi, we've got 3 pi on 2, and that's going to be a stationary inflection, right?